Now in this video we're going to look at spearman's rank correlation coefficient. So what I've got here is I've got some tomato plants, 2, 4, 6, I've got 8 tomato plants altogether, so n is 8, and I've got judges to rank them amongst the most perfect looking tomatoes that there possibly are. So Judge 1 thought A was fabulous, Judge 2 thought A was not so fabulous because it's 7 out of 8 they've ranked it. But they thought that G was fabulous, but then Judge 1 didn't think that G was fabulous. And so looking through the numbers, the two that I've looked through, it looks like they're disagreeing. Now, obviously I could do product moment correlation coefficient to find out the actual value, and if I did my PMCC, SXY over SXX square rooted times SYY square rooted, and filled out all of these values, then I will actually come out with a value. And the value that I come out with is minus 0.690. Now, I'm not going to show you all of that. You know how to do it. I did it on computer, came out with that value, Bob's your uncle. However, the reason I've put the value down is because actually, although it does give us a measure of correlation, it's quite a lot of work to add up all of those. And so what we can do here is actually make it a lot easier for ourselves. And to do that, what I'm going to do is end up using this table to have certain extra few values. Now, I'm going to do this in green so you can see the difference. And this, remember, was our product moment correlation coefficient answer. So what I'm going to need to do is have a nice little formula. And the nice little formula for spearman's rank, our S, comes out to be 1 minus 6 times the sum of your difference squareds over n squared minus 1. And so this is the values that you're looking for. You're going to need n, which we've got. You're going to need the difference between the rankings, and it's very important because it's spearman's rank. So these are already ranked, and so is that one. So the difference between 1 and 7 is 6, 8 and 2. Now, 1 take 7, really I should put a minus 6 in there. 8 take 2, a plus 6. You could do it the other way around, but ideally when you're doing these you want to be consistent. And so what I'm going to do is I will call Judge 1, let's call them X, Judge 2, we'll call them Y. Look at the ingenuity here. So we'll call this X, this Y, so that's going to be X minus Y. Now don't worry about it because actually we square them in the end, so this will be X minus Y squared, which gets rid of any negative values. No, wrong way around. So we've got 6, 4 take 3 is 1, 6 take 4 is 2, and I will complete the rest of this including the d squareds. So minus 6 squared is 36, 6 squared is 36, and let me finish it off. There we go. So that gives me a total of 142. Now all I need to do is shove all of that into this formula. So 1 minus 6 times 142 over 8 lots of 8 squared, which is 64, take 1. Now, generally speaking, what I tend to do is I stick this bit into my calculator first and then press equals. Obviously, you guys have the nice fancy calculators, so you might be able to do it all at once. And you should get an answer of minus 0.690. And sure enough, that's exactly the same as the product moment correlation coefficient. So the question would be, well, what's the difference between the two? Well, obviously, if you've looked at the previous examples, you'll know just the volume of work I have to do here is much, much less than the volume of work I have to do for the product moment correlation coefficient. And spearman's ranking relies on having the rankings first. So Judge 1, I don't know what score they gave, I just know they rated it first. Judge 2, I know they rated it 7th, but not the score. So if you have the actual raw scores, then you'd err towards the product moment correlation coefficient. If you only have the rankings, then you'd err towards spearman's rank. Now, generally speaking, why would you collect the rankings and not the original data? Well, in competitions is a prime example. Other examples would be if you have to collect a lot of data. Let's say you had to collect everyone's heights in a class. Well, actually, measuring them all, getting them all to do that would take quite a long time. But if you say, right, everyone get in order, and then just take who's first, who's second, who's third, then you don't need their exact heights. You don't need the errors that come with the exact heights. You know who's first, you know who's second, you know who's third. Now, after this, have a look at example 4.3, because it relies on spearman's rank, but it also looks at hypothesis testing with spearman's rank, which is pretty similar to the product moment correlation coefficient hypothesis testing, but there is what's the word I'm looking for? There are different tables for it, so they don't use the same tables, and that's quite important. Now, one more point that I want to make is what happens, for example, if you get same rankings, and that's quite a problem because actually it's quite common. So if I do just 4 tomatoes, A, B, C and D, and we'll have rank 1, rank 2, and rank 3, well, herein lies the problem. Now actually it's not rank 3 that I have there, it's actually going to be rank 4, because this is joint second, and therefore if you joint second, effectively it was between second and third. So what I have here is 1, 2, 3, 4 altogether, but a joint bit here. Now because they're between second and third, I don't know whether it's going to be second and third or third and second, so what I end up doing is finding out what's halfway between them. So I use that 2 plus 3 over 2, which comes out to be 2.5. So my actual rankings that I'll then write down is A was first, B was second and a half, C was second and a half, and D was fourth. And I wouldn't actually have the value 3 in there, I'd have left that out because they're joint second, joint third, technically at the same time.